As you can see from the title of this lesson, this tutorial is about the properties of matter. We have just finished the discussion about what matter is in the different classifications and states of different matter they are: solids, liquids, gases, elements, compounds, mixtures. This discussion gets us into how is it that those things can be changed, and how is it that when they are changed we decide what to call those things that have happened. If we're going to get into properties of matter, there's two major property categories that you'll find. They're called extensive properties and intensive properties. Again, very similar in the chem world. You take two words that look very similar, but they mean 100% different things. An extensive property is a property that depends on the amount of matter that is present. The more matter that is present, the more of a higher number that will be measured in. For instance, mass, volume, or energy. If you take a bowling ball and get its mass, it will give you a certain number. If you take a bowling ball that is 4 times the size of the original one, it will give you a larger number for its mass, because mass is extensive. The more matter you have, the higher that number becomes. Volume is the same thing. If you take somebody my size and measured our volume through water displacement, you would get a certain amount. If you took somebody, a little taller, a little more muscular, you would get a much larger numeric value for their volume, because it is extensive. The more of it you have, the higher the number becomes. On the other hand, you have intensive properties. An intensive property does not depend on the amount of matter that is present. It does not matter if I have a cup of water or a gallon of water, right, for something like its melting point. Right? If you go to boil a pot of water or you boil a glass of water, they will both boil at 100 degrees Celsius or 212 Fahrenheit. They will both freeze at 32 Fahrenheit or 0 Celsius, because that is an intensive property. It doesn't matter how much of it there is, it simply matters, okay, what it is, the identity of the material. Other intensive properties include things like color, density, or conductivity. And to highlight it one more time, if I were to take a piece of copper, right, that was a string wire, right, and stick it into an outlet, I would get electrocuted. Right? If I similarly took a piece, right, that was much, much, much larger, and I were to get standing on it and it were struck by lightning, I would still get electrocuted, because it doesn't matter if I have a lot or a little of it. All that matters is if it is copper, it conducts because it's intensive. And we'll get into that. Anything that we tend to measure extensively for the most part, because we need to know how much of it we have. Like things that tend to be intensive properties, we find them once and then we can look them up based on who they are. I don't need to go to the back and boil a pot of water every single time I want to find its melting point, because I know it's going to melt at 212 degrees Fahrenheit, 100 degrees Celsius, because it doesn't matter how much that there is. So once you get through these two big classifications of properties, you'll get into some more specific ones. The two that we're going to focus on here are physical properties, which lead to physical changes, and chemical properties, which lead to chemical changes. A physical property or a physical change is one that can be observed or measured without changing the identity of the material. I can change its shape, I can change its size, right, but I cannot change who it is. Some good examples of physical properties or physical changes are things that are changes of state. Melting something, taking a solid and turning it into a liquid. If I take an ice cube, its formula is H2O. If I melt it and I have a glass of water from that ice cube, its formula is still H2O. I did not change who it was. I didn't change its identity. I simply changed what it looked like. It went from a cube to a liquid. Boiling is the same. Right? I have a liquid, I put it on the stovetop, I turn it into steam. Right? Steam and water are both H2O. They simply look different because boiling something is a physical property for a physical change. Right? Density is a physical property. It does not change the identity of it to check its density. Mass is a physical property. Right? I measure it, it's physical. Right? If I change something's mass, I can do it without changing the identity. I take a piece of grapefruit, put it on a balance, I cut that grapefruit in half, I put it on the balance, I lowered its mass without changing its identity. It's a physical change. Chemical changes, on the other hand, cannot be done without changing the identity of the substance. A property that pertains to a substance's ability to transform into something different. You start with substance A, it turns into substance B, right? And its ability to do so is a chemical property, and the process of doing it is a chemical change. Two good examples of that are flammability. Right? If something is flammable, meaning it's able to be burned, that's a chemical property because once I burn it, it is no longer what it originally was. Right? A piece of wood has a certain formula, right? Or a mixture of formulas. When I burn it, the new substance that I get has different formulas. It is a change in formula. Reactivity is the same thing. If I mix two things together, right, an acid and a base, right, we know that that's called a neutralization. Right? I take the acid, which has certain properties, I take the base, which has certain properties. When I mix them, I get a salt and a water, which have totally different properties because those reactivities are chemical properties, and the reaction is a chemical change. So the big thing to remember, chemical changes result in a new formula of a substance. Physical changes, the formula of a substance or a mixture or an element remains the same. Cooking is another great example of a chemical change. Anytime you undergo a chemical change, we can represent it by what we call a reaction. A reaction is a process by which one or more substances are changed into one or more different substances, as I was saying with this chemical change. A chemical reaction and a chemical change are one and the same thing. We can represent any chemical reaction with an equation. And an equation represents, with symbols and formulas, the identities and relative amounts of reactants and products in a reaction. Think of a chemical equation as a recipe for having a reaction occur. Just like you have recipes to cook things in your kitchen, you also will have recipes to create certain chemical reactions. Right? If we take eggs and flour and butter and pancake mix and we mix it all together, we get pancakes. We do the same thing with equations. Right? The recipe tells you how much egg, how much butter, how much pancake mix. A chemical equation does the same thing. It tells us who participates in the reaction and in what amounts we need them to make the reaction occur. All reactions will possess the same type of equation characteristics. All reactions have what we call reactants. A reactant is a substance that undergoes a chemical change. When we write a formula for a reaction out, the reactants are always on the left side, which is why you'll notice reactant and its definition are in red, and the two formulas of our reactants are in red on the left side. And on the left of what? It's on the left of what we call the yield sign, which is always an arrow. Products are the things that are about to be formed. Products are the substances that result from a chemical change of reactants. They are always on the right side of an equation, which is separated by that yield sign. In this case, CaSO4 and NaNO3 are our products, which is why they are in green to match your product definition. If I looked at an equation like sodium sulfate reacting with calcium nitrate, those would be my reactants. and they form calcium sulfate and sodium nitrate. Equations also account for the relative amounts. So it tells us how many sodiums, how many sulfurs, how many oxygens, right? And then you'll have numbers in front if you need more than one of those substances. So all chemical reactions look like this. The other thing you may see a chemical reaction include is a little set of parentheses after it with abbreviations. Those abbreviations are simply telling you what state it needs to be in. Solid, liquid, gas, or you'll get into a new term that we call aqueous, which means it is dissolved in water. But all chemical changes have reaction equations that are associated with them. Now, knowing something is going to occur is great, and predicting what it's going to make is even better. But when we get into the physical laboratory, the most important thing is knowing, has it happened yet or not? Has it occurred, or am I still waiting for it to happen? Otherwise, we could sit back in the lab forever. So the last thing I really want to focus on are the signs of a chemical reaction, or the signs that a chemical change has occurred. There are 5 different signs of a chemical reaction, and I'm going to show you each of the chemical reaction signs so that you have a visual representation of, well, what does that look like? How do we know what that is? First one is the evolution of heat. Evolution of heat means that some heat is given off, or on the reverse, the need of heat, something getting colder, would both let me know that a reaction has occurred. It's a sign that something's happened. It got hotter or it got colder. Evolution of light. If I take two things together and light is being given off, that is a sign that a reaction has happened. The production of a gas. If I see the formation of a gas occur, that tells me something chemically has reacted. And if there's any type of liquid involved, that's usually easy to spot. It involves bubbles. The fourth sign of a chemical reaction is called the formation of a precipitate. And a precipitate's a word we haven't talked much about. All a precipitate is when two liquids react together to form a solid. Or, in general, two things react together and one of the products is a solid that reforms. Last but not least is a color change. A lot of times when you form a precipitate, the precipitate will be a different color than whatever the reactants are, so it will lead you to a color change. Color changes do not always mean that a chemical reaction has occurred. That's why I have an asterisk here that says sometimes. For instance, if I put food dye into water, food dye into water is not a chemical reaction. Even though it looks like there was a color change involved. I took, clear, colorless water and I put food dye in it, and now I have clear blue water or clear red water, and so on and so forth. So like I said, I'd like to show you an example of each of these so that you can see what these signs of chemical reactions look like. So I'm going to put on my goggles here. I'm going to bring out a few things that can help us with the demonstration. So this here is just going to elevate us so that you can see what's going on. And I'll do my best to go in order there for you. So the first thing I'm going to bring out is a very large matchstick. Now, believe it or not, a lot of everyday simple tasks that people do involve chemical reactions that you take for granted. You don't know what the chemicals that are involved are, you just know that one has happened because you see the evolution of heat and light. This first demo is going to highlight both of these. When I take this match, which has a tip of red phosphorus, which is P4, and I strike it on the surface of the match striker, a chemical reaction occurs where the red phosphorus turns into carbon dioxide, in a reaction where hopefully we'll see our first two try again. see our first two signs of a chemical change. Obviously, you can see that light was being given off in this process, and if while this match was lit, I were to stick it into my hand, I think we all know that that would be very painful because there's a fairly large amount of heat that is involved with that as well. The light isn't what hurts me, it's the heat that gets transferred into my hand that causes the burning process. So, evolution of heat, evolution of light are two of your signs of a chemical reaction. Right? The third one, production of a gas. What I have here, right, is a graduated cylinder full of hydrochloric acid. And what I have here is a beaker that has some zinc in it. And I'm going to turn the light on, and hopefully this comes out as well on the video as it does in person. Right? And what I'm going to do is I'm simply going to take a few pieces of this zinc and put it in with the hydrochloric acid, and I'm going to let those two things react with one another. Hopefully you can see right here that you are seeing some fairly vigorous bubbling going on, especially if you look toward the top of the graduated cylinder here, because what's going on is the zinc is reacting with the hydrochloric acid. Now, we'll get into this type of thing much, much later, but what you'll understand is that we're forming two new compounds. Right? One called zinc chloride, and the other, right, is the element hydrogen being released. Hydrogen is a gas, and the hydrogen is what tells me the reaction is occurring, because that is the bubbling that I'm seeing come out in this particular liquid. And if there were no liquid present, it would be a little bit tougher to determine if the reaction was occurring. I would have to try to trap the hydrogen bubbles, all right, in a container, and then I'd have to test it in other ways to see, oh, did we produce hydrogen? And so I'm going to take this one and I'll set it off to the side, but that reaction will continue to go. Another sign, like we said, was the evolution of heat. If you were to be in the room with me here and you were to put your hand on this, you would notice that this graduated cylinder had gotten very warm at this point. If it had gotten cold, that would have been equally significant in telling us that a chemical reaction had happened. My fourth sign of a chemical change is the formation of a precipitate. And what I have to help with that, again, is another graduated cylinder, because they're a nice size here for what we're doing. And I have two other graduated cylinders that have different substances in them. The one here on the right is potassium iodide. The one here on the left, right, is lead 2 nitrate. So what happens here is I'm going to put this into an empty graduated cylinder, the potassium iodide. And I haven't had any reaction occur yet. There's no bubbles, there's no heat, there's no light, I haven't had a color change, I haven't seen a precipitate at this point. I haven't seen a solid form. Now I'm going to add my lead nitrate. And what you'll see, hopefully, is that what was two perfectly clear, colorless solutions, that when I put them together, created something that was most definitely not clear and colorless. We got a yellow color in our reaction vessel. The reason we get that yellow color has to do with the reaction that occurs there. I took potassium iodide and I reacted it with lead 2 nitrate, and what we get is lead 2 iodide and potassium nitrate. And the yellow substance that you're seeing is solid lead 2 nitrate, lead 2 iodide being formed. if I had the time to let this sit and settle out, you would notice that it is in fact a solid. It would all crystallize and fall to the bottom, so that at the end of the day, and when we do this in class, I show it to you over 2 days, you would see a clear colorless liquid on top and then a bunch of a yellow powder that had now settled to the bottom. Right? That is a precipitate. When I take two substances, react them together, and I get a solid. Many times that involves a color change because the solid absorbs light at a different wavelength and reflects light at a different wavelength than the original substances did. Right? So these are your signs of a chemical reaction. Right? If you see one of these things, you know a chemical change has occurred. The last thing I wanted to talk about very briefly has to do a little bit more with this idea that we can have heat involved in reactions. So I'm going to move my demos off to the side here. And heat gets involved in reactions in a bunch of ways. We have what we call endothermic reactions or processes and exothermic reactions and processes, because reactions and physical changes could also need or give off heat. An endothermic process is a chemical or physical process where heat is needed to occur. Right? Endo, the prefix endo, means within, needs to come in. Thermic always means heat. Examples of endothermic processes are melting ice. If I want an ice cube to become water, I need to give it heat. I need to warm it up so that it can break the intermolecular forces, allowing it to turn into a liquid. Cooking food is an endothermic process. If I want to bake chicken, if I want to make a pie, right, what do I have to do? I have to put it in my oven. My oven gives it a lot of heat, right? It absorbs the heat. It's an endothermic process. Exothermic is the exact opposite. Thermic still meaning heat, but the prefix ex or exo, exit, exile, always means going out, being moved out. Exothermic is a chemical or physical process where heat is given off. Examples of exothermic processes would be the burning of the match that I showed you. Heat was given off during that reaction. And one that confuses people is freezing. If I want liquid water to freeze, the water needs to give off heat to get cold enough to freeze. Most people think of it as cold being absorbed. It doesn't work that way. If something feels cold, it's because a lot of heat, all right, has been released, all right, from it or taken in to it. All right? So freezing is an endothermic process, right, because the water, exothermic, right, because water has to give off heat to turn into ice. Steam turning into water is an exothermic process. Right? The steam has a lot of heat and a lot of energy. It needs to cool off or release heat to turn into water, so it's releasing heat. It is exothermic. Right? So the big thing to remember is that endothermic things need heat, exothermic things give off heat. Most of the time, exothermic things feel warm to the touch, endothermic things feel cold to the touch, but I try to highlight some exceptions to that so that you can think about things in terms other than just that is hot exo, cold endo. Just think, is it leaving or is it coming in? So this was a bunch of information about types of reactions and signs of chemical changes. I hope it helped you out. As always, if you're still confused about anything or you are wanting to find out more, please do not hesitate to stop in and ask.